we've been talking about ANOVAs for a couple classes now. And I've showed you like how to do the ANOVAs. And then the homework that I was trying to make for the last class, I created this data set. Actually, you can start grabbing the data right now. If you go to WNAP.com under the classes, I already have the data set for today uploaded on that. So you can just right-click that link and save it. All right. Anyway, so I made this data set, and I was so proud of myself. And I'm like, okay, they're going to analyze this. And then I started doing the analyses and trying to write the questions. And I'm like, oh, I'm going to have to show them how to do more things. And oh, this is going to be hard. So I revised the homework. So hopefully, if anyone took a look at it, it's much easier than what it would have been. And today I'll show you how to do it the way that you would have needed to do it if I had made this your homework for last time. And I'll show you the easy way. The way that you can really take advantage of R. So go ahead and get the data, Stats Lab 07. Set your working directory, load the data, and then let me know when you're ready. Got it? So some of you guys may have noticed that I changed the way that like I had the data. So before, like when we were doing t-tests, I had like one row for one sample and another row for a different sample. And then like recently I've had one column for one sample and another column for another sample. And recently, I've had like everything in one big long column, all the data, and then I say, okay, you need to use the other columns to figure out which piece the data belongs to. The reason that I'm doing this is because when you're doing R, or when you're doing ANOVA, R likes things to be in a particular format. So I've laid the data out so it's in the format that R likes. Does anyone not have the data loaded up at this point? We're all good to go. Okay, so we've got the data. Now, let's do it the hard way. You can find the code, how to do this, on my website. I don't want you to work along with me. Just want you to watch. I'll explain a couple things, but check it out. So, for the last couple of classes, I've told you how to get the sums of squares, right? Okay, so you're going to take this mean and subtract the grand mean from it, and then square it, and then multiply it, and then add all that up. And this is a pain in the butt, especially when you're dealing with very high level interactions. Ox, stats. Where are we? Stats lab. Voila. Okay. So the first thing I have is I set the working directory, make this bigger. I loaded the data, and then you can look and see how the data is structured. So if you did that, you see that it's a data frame. It's a data frame. It has RT, which num it means, so there are a bunch of numbers there for RT. Then it has TF, which is a factor, and it says it's a factor with 2 levels. So just by using stir on a data frame, it can tell you if you have factors, and if they are factors, how many levels there are. So just with this information, like we have enough information to compute degrees of freedom. How many degrees of freedom do we have for TF? So it's a factor with 2 levels. We have 1 degree of freedom. How many degrees of freedom do we have for DS? 2. We have 3 levels. 3 minus 1 is 2. How about for TP? 1. Okay, great. How many would we have for the interaction between TF and DS? 4?
3.
3? 1? 2? So we basically run the gamut. Now, if you Hopefully the person that said 3, they were thinking, well, I remember him telling us that to get the, I can't speak right now, to get the degrees of freedom for the interaction, all you need to do is multiply the degrees of freedom for the factors that are involved in the interaction. So if we're talking about an interaction between TF and DS, well, we have 2, so we've got 1 degree of freedom here, 2 degrees of freedom here, 1 times 2, that's 2. It's not 3. So, not the person that said 3, the person that said 2, whoever said 2. Alright, good job. Alright. Same thing, for the 3-way interaction, we have 1 times 2 times 1, so we also have 2 degrees of freedom for the 3-way interaction. Alright. Now, let's look at some of the things that I did. So I did something here to calculate the total number of participants. So the total number of participants, I can just get the length of all of the observations that I have. That's RT. Maybe I should talk a little bit more about this data first. Did anyone do the homework that was put up last night yet? Awesome. Yeah. Alright, so the homework for last night is based off of this very famous cognitive psychology experiment done by Treisman and Galat in 1980. What they were interested in is how different factors affect visual search. So they had people looking for target letters, and the target letter was going to be a letter that was different from all of the other letters. Now they varied a couple things. So if you look at the R, you see there were 3 factors. TF indicates the features that are in the target. So what is a feature? A feature is something like color, size, shape, things like that. Now, the target, the letter that they were looking for, could have a unique feature. So maybe everything in the display was green and the target was red. Now, how hard would it be to find one red object amongst a whole bunch of green objects? Would that be hard or easy? Unless you're colorblind. If you're colorblind, it's going to be hard. If you're not colorblind, you're looking for the one thing that's different, right? So if there's one red thing and everything else is green, how easy would it be to find the one thing that's different? Imagine you are in a garden. And the garden is green, and there are all the plants, and you want tomates. And the ripe tomates are red. Is it hard to find the ripe tomates? No. It's really easy to, if there's just one red one, it's like, oh, there it is. Okay, right? It's really easy to find something when it has a feature that nothing else has. So there are 2 levels, common and unique. So unique means that the target has a unique feature. So it should be easier to find. Common means that it shares features with all of the other distractors. Okay? The next thing is DS. This stands for display size. So display size. You are looking at an array of objects. So there are a bunch of letters. Display size is the number of letters that are there. So with 5, I have 0, 5, because otherwise R throws a fit if I just say 5. Anyway, so 0, 5, this means that there were 5 letters in the display. 15 means there were 15 letters in the display. 30 means there were 30 letters in the display. Imagine you're looking for a friend, okay? If you are going to find your friend at the cafeteria, and there are 5 people in the cafeteria, one of them is your friend, is it easier or harder to find your friend than when there are 30 people in the cafeteria? It's going to be easier with 5, right? Okay, and the final factor, TP, this stands for target presence. This means, was there one unique thing in the display or not? If there was always one unique thing in the display, you wouldn't even have to look for it. You would know it's always there. You just say, yes, 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 as soon as it pops up. But by having it there only sometimes, you have to look for it to be able to determine whether it's there. So we have 3 factors. the features of the target, the display size, and target presence. Okay? So,
Professor,
yes?
Why is the difference like, for the last part of it? Like we have 2, 2, 2, but for the middle we have 1, 1 and 2, 2, 1.
It's just the way that the data frame is ordered. So if you, let's do this. So, data 1, 10. So this will give me the first 10 items in the data frame. Undefined columns like this. What do I need to do? Yay, there we go. Okay. So if we look at the first 10, we have the RT. RT means response time. How long it took someone to indicate whether a target was present or absent. Okay? So these are response times. TF, this is the features of the target. Notice it's unique, 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 unique. Okay, up here we have factors with 2 levels, common and unique. It sorts the letters, or the levels, like alphabetically or numerically. So common comes before unique, right? C is before unique. But the first values that we have in our set are unique, 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 which responds to here, the second factor. So 2, 2, 2, 2, 2. Here, we have 3 levels. S05, S15, and S30. Notice that these are all corresponding to the first of those. Thus we have the 1, 1, 1, 1, 1. And then 2, 2, 2. So 1, 2, 3, 4, 5, 6 ones, and then 2. 1, 2, 3, 4, 5, 6, and then it moves up to the next one. Same thing for TP. So present, absent comes before present, so present is 2, and we've got all of those are for present. Okay? That's why you have the 1s and the 2s. It's just indicating which level of a factor that this observation comes from. So each row here indicates one observation. This was an observation for someone who was looking for a target that had a unique feature in a display size of 5 letters where the target was present. Okay, so some of the things that I would need to calculate all of the sums and squares and the mean squares are things like the total number of observations that we have. So to find the total number of observations, I just got the length of our RTs. So then I wanted to find the number of levels for the target feature. Now we saw that it tells us automatically, but if we didn't know how to get that from STIR, we could calculate it. Get the length of, look, I said levels. Levels data TF. So if I say levels of basically this, so that is levels of TF here, what it does is it looks through the vector and then it finds how many different levels that it has. And I just took the length of that. So we've got 2. So I found the total number of subjects, I found the total number of levels for our first factor, for our second factor, for our third factor. I figured out how many different conditions we have. That's just the number of levels that we have for each factor multiplied together. And then I have the N, which is the number of observations per condition. Well, if we have, so we have 2 levels of the first factor, 3 of the second, and 2 of the third. So that's 2 times 3, 6 times 2, it's 12. 12 conditions. Now, in an ANOVA, you want a balanced design, right? So you should have an equal number of observations per condition. So if you know that, you can figure out how many observations you have in a condition by dividing the total number of observations by the number of conditions that you have. Post-hoc is blue. All right. So then, all I did was I found the degrees of freedom. Right? So this is all standard stuff. Degrees of freedom for the total is just the number of total observations you have minus 1. Degrees of freedom for the error is the number total minus the number of conditions, yada, yada, yada. I found the grand mean to make it a bit easier for some of the other calculations. Then I started finding sums of squares. Let me put all of this in here so I can work with it.
Can you go 2?
No, I would prefer not.
And we'll slow down the shipper, right?
All right. So we have all that in there. Then what I want to do is I want to find some sums of squares. So the total sums of squares, that's just the difference between each observation and the grand mean. Sum up all of those differences, or sum up the square of all of those differences, and you get the sum of squares total. For the sum of squares for our first factor, what I am doing is I'm taking the mean for the particular level of the factor. So if you guys remember back to like the first statistics lab, we talked about using logic in R. So if you just look at the first part, well, that's just the RTs, the response times that we're going to be dealing with. This part in here tells us which RTs that we want. So we want the response times that correspond to a display size of SO5. Okay? So this is going to get the mean response time for the level of display size 5. Okay? And we will subtract the grand mean from that, square it, then we're going to get the mean of the next level.
Will you add up? Will you add all of them?
Yeah, because it's a sum of squares, so we're adding all of these individual pieces together. So then we get the mean for the response times for the next level. Then we get the mean for the response times of the next level. We add all of those up and then we multiply accordingly. Because here we're taking only one mean minus the grand mean. But remember, we need to represent each observation that was within that level. So we need to multiply by the number of observations that we have in that level. So the total number of observations that we have, that's n, the number of conditions that we have, times the levels of our first factor, times the levels of our second factor, times the level of our third factor. But since we're interested in a particular factor here, we are going to take that out of this part to get the number of observations for our particular mean. Yes, Cameron. Thank you. Okay, so this part isn't really that hard. But the interactions get a little bit harder. So I get down to the interactions. And now I need to get the mean of the response times where the condition is a unique feature and a display size of 0.5. And it gets more complicated for the three-way interaction. And remember, we have to subtract the sums of squares for the factors that are within the effects and the smaller sums of squares as well. So this is just a huge mess, which is why I decided not to have you guys do this for the homework last night. Okay, so let's load this up. Boom. Whoo! Okay, now let's see if what should be correct is correct. So the sum of the squares total should be made up of all of the other sums of squares, right? So what I did is I took the sum of squares total and I subtracted all of the other sums of squares from it. Now because we're dealing with so many numbers and R only has a finite amount of precision, I took the absolute value of this and I wanted to see if it was less than 0.001. It should be 0, right? But because of rounding errors, it's probably not going to be exactly 0, so I did that instead. And I'm also going to indicate which each of the sums of squares terms are. So, boom. Look, true. So, the sum of squares total minus all the other sums of squares is some very small number, right? It should be. It should be very close to 0. And then I have the individual sums of squares up here. Okay. Good grief. That was a pain in the butt. That was a hard way. Now I want you guys to do this. AV equals AOV that.
How will we do this?
In the English, American style, it's right here. I have no idea what it is on the church keyboard. Did anyone find it?
Yes.
Alt N. Okay. The poor students that aren't here on the test, they're going to be like, how do I do that? Oh. She says. What do you see?
TP value, degrees of freedom, sum of squares.
You see something like this? So sum of squares, degrees of freedom for TF. So this is for our factor, the target features. We have the sum of squares for the degrees of freedom. Same thing for DS. Same thing for TP. She's clapping because she loves R so much. It's funny, SPSS, like there's a lot of click, 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 clicking. And if you want to do other things, you need to click, 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 click some more. Unless you know how to program in SPSS, which is actually a lot like R. So save your money and just use R. Okay. Now, the question is everyone got this?
Yeah.
Good.
Not the same.
Not the same.
Yeah.
Should be...
No, okay, same.
Same? Alright. So the question is, do these equal the things that I calculated before? So you can keep that on your screen and compare them to the values that I got for my different terms. Let me bump up the size here so you can see it better. So,
It's rounded.
GUI preferences. So it should be pretty close. Said it's rounded, but if you do the rounding, you get the same thing. So you should see that the values that you came up with using that AOV got you basically all of this information, plus the degrees of freedom. So you didn't even have to go through all that stuff that I did to calculate the degrees of freedom. So now what can you do? You know all the sums of squares, you know all the degrees of freedom.
You can find F.
You can find F. How do you do that?
Means.
You need to get the mean squares. How do you find the mean squares?
Sum of squares divided by the degrees of freedom.
That's right. So the sum of squares, let me put in, get caught up with you guys. AV. So all I need to do to find the sum of squares for each of these is divide this by that. That'll give me the, or not the mean sum of squares, the mean squares. So I can find the mean squares for display size, just divide this by that. For target presence, divide this by that. For our interactions, it's all the same. Okay, so we know how to get our mean squares. Then how do we calculate the F?
Divided by mean of squares error.
We divide what by mean of squares error?
Effect.
Yeah, we look at the thing that we're interested in. We want to look at the effect of the target's features. So we compare the mean squares for this to the mean squares for that. We divide the mean squares for this by the mean squares for that. That will give us our F, right? And we already know how to calculate the critical values for F, right? QF, quantile F, for our alpha level, actually 1 minus alpha. And then we give it the degrees of freedom for the numerator and the degrees of freedom for the denominator. Pow! Sweet. Now R is pretty cool. Oh, yeah. All right. Yes.
Which one is mean of effect, and which one, like how we will see that? What is the?
I don't understand the question.
Like we told that we will find F, but here, which one is the mean of the effect?
Well, so we have multiple effects, right? We actually have 3 main effects and 4 interactions, right? These are all main effects, and these, the rest of these, are our interactions. So we would have potentially 7 different Fs. We would have an F for each main effect and an F for each interaction. Now we need to compare the Fs that we get with the appropriate critical Fs, with the appropriate degrees of freedom for each of those pairings, in order to determine whether each of these main effects is significant and whether each of these interactions is statistically significant. So we're going to be doing a bunch of F-tests, right? Because I said that the ANOVA addresses the question, are any of these effects significant, or are any of the interactions of those factors significant, right? Okay, so let's take a look at AOV. So AOV, what does it stand for? Analysis of variance. Yeah. So I passed it 2 parameters. I gave it a model that describes the relationship between the dependent variables and the independent variables. And I gave it the name of the data frame that contains all of that. So let's take a closer look at the model that I used. So this is the model. This thing here that you specified, that's actually a model. So there are different parts to the model. The first part, RT, what's that? Everyone should be able to get this. Response times. It's our dependent variable, right? RT is our dependent variable. Now this little funky symbol, which I believe is called a tilde, means our dependent variable is modeled by. So this means that the dependent variable is modeled by, or is predicted by, right? We're making predictions, right? That's the whole point of statistics. What's the best estimate of someone's response time? Well, if we know the grand mean, that's all we have to go with. If we know the grand mean and the effect of some factor, and we know what level of the factor they are, we have a better prediction. So we are predicting response times off of this. This is our model. So what is that? TF, these are our independent variables. And there are independent variables for target feature, display size, and target presence. And when we use these asterisks, what we're saying is we want to get the effects of each of these factors and the interactions between all of these factors. Right? Every combination of the interactions that we could have. So by using this, R knows to get all of those different pieces. Now we don't have to use that. We can create other models if you have different questions. So let's talk about main effects only. So we could say that RT is modeled by the main effect of target features, by display size, and by target presence, but not by any of the interactions, right? So the plus means we're just going to use these terms only. We're not going to multiply them and get any interactions. Just use those terms only. So go ahead and try that.
It comes like 3 sum of squares, each of them, and their degrees of freedom.
Yeah, so you get sums of squares for each of those, and degrees of freedom for each of those. You don't have an interaction. And if you notice, the sums of squares and the degrees of freedom for the main effects are the same, but the error term, that is the residuals, are different. Right? Why? Well, because we're only making our prediction off of these. If we're only making our predictions off of these, we're not going to have as good of predictions as if we included the interactions of those, right? So if we are not including some other things that can allow us to predict, we should have more errors in our predictions, right? That's what the residuals are. Like a residual, think you take a shower and then you leave, and there's a residue on the shower wall, right? It's what's left behind. So the residual is basically what's left behind after the model's made its predictions. Those are the errors. Okay, now if we just want the interactions, we can tell it to just get the interactions by using colons. So try this. So I'm going to get the interaction between target feature, display size, target feature, target presence, display size, target presence, and the three-way interaction. But I haven't just put the main effects at all anywhere. So the main effects won't be included. Oof. So, I know some people are done. You can notice that a lot of the terms are different from what they were for that first analysis. Only the last three terms should be the same as our first. Why would that be? Well, remember, initially when we were calculating these, we took out the sums of squares for the factors that were involved in those, or the interactions of the factors that were involved in those, right? But here we don't have sums of squares for those first couple things. So we can't take it out. So that's left in. Now, you might do this if you had a good theoretical reason. Perhaps you knew of some factors that had been well established that they don't have any effect. And if you thought, well, okay, it's well known that these don't have any effect by themselves, but you have a question about whether they actually interact, then you could do something like this, which is basically saying that we have no reason to think that the factors by themselves have any effects, so we're just going to lump them in with the rest. Okay, so we could have said this. Don't do this, just look. So we're saying response time is predicted by the main effect of target feature, the main effect of display size, the main effect of target presence, times all of those interactions that we just did. So that would give you that whole big first thing that we had, much, much simpler with that. So we'll stick with this. So if we go back, we give all this data, right? We already talked about how we can use this data to calculate the mean squares and then calculate F ratios from those mean squares. Now, we can use another cool function, summary AV, to do some cool stuff for us. So that AOV just gave us the sum of squares and the degrees of freedom, and we would have to calculate all of this stuff by ourselves. But, yeah, if we do summary AV, all of that hard work is done for us. That's so nice. So now analyzing this data set's easy. If you went through and you did all of those like individual means, like I was trying to analyze the data, and it took me hours doing it the hard way. And I was like, why isn't this working? My formulas are right. My formulas are right. I made a stupid little mistake. I missed one letter. I screwed up one letter. And I was getting the wrong error. And it took me hours to find this stupid one letter.
Just like us.
Just like you guys. Just one little thing off. So this decreases your chances of making a silly mistake like that. Right? Okay. So this is pretty sweet. So you've got 3 steps. You need to have the data in the right form. For this class, typically I'll provide you the data that's basically in the right form. If you notice the form of the CSV file, if you've actually opened up the CSV, you see how I have like each row ordered. This is exactly how I set up my files when I'm collecting data. I say which condition it's from, using the different levels of the different factors, and then I say what the dependent variable, the observation of the dependent variable. So if you join my lab for directed research, which some students have. If you start looking at some of the data that I've collected, you will see things in exactly this sort of style, which lends itself very easily to analysis of variance. So you get the data in the right form, then you use AOV with the appropriate model, and then finally you can use summary to summarize the results. It's super easy. Okay, questions? So that covers our factorial ANOVAs, right? I didn't talk about one-way ANOVAs yet. Could we do one-way ANOVAs? Maybe. You guys have already done a one-way ANOVA, and you haven't even realized it.
Separately with some symbols. Is it one way?
Ooh, actually, I'm sorry. You came very close to doing it. So I was thinking about this, but in my mind, I thought I only gave you one of them as opposed to all three. If you wanted to do a one-way ANOVA, you can just give it one factor, right? The factorial ANOVA has multiple factors. So we have multiple factors here. So the one-way version of this, you just include one of the factors. So I thought you did it. In my mind, I'm getting old. It's probably on the next slide. All right, here we go. So all you need to do is specify the right model. So imagine that we had the response times and the target features only. What model would we use?
What? TF?
Okay, TF. But the model isn't just TF. Right? The model is something.
Yes. Response time?
RT?
TF.
TF. That's the model that we would use. All right, let's see. Oh, yeah. All right, so do that. Notice I combine both of these things into one step.
Degrees of freedom, sum of squares.
You get the degrees of freedom, the sum of squares, the mean squares,
F value.
F value, and the P value. All of that, one fell swoop. And look, it even tells you how significant it is. Or basically, if you use a certain alpha level. So if you used an alpha level of 0.05, you would have this star. Notice there are two stars. Well, that corresponds to a 0.001 level of significance. So if you had a 0.01 alpha, you'd reject. Actually, you don't need those stars, because you can just look at the value for yourself. But it's there. Lots of times in graphics, you will see things like 1 star or 2 stars or 3 stars to indicate visually how significant or what level of alpha the data go beyond. Okay, so let's talk about a two-way factorial ANOVA involving target presence and display size. So we did a three-way factorial ANOVA involving 3 factors. Now how about a two-factor ANOVA? What would our model be?
TP.
Yes.
TP?
No. Yes.
This.
What is it?
Yes.
Go ahead, try. Do you get something like that?
Yes.
So, which of the effects are significant?
Second one.
Second one?
First one.
First one, second one, is the third one?
Last.
We need to know what the alpha is. If we're dealing with an alpha of 0.05,
0.01.
all of them are significant if we're dealing with an alpha of 0.05, right?
0.001.
If we were using 0.001, this would be significant, this would significant, this would not be statistically significant, right? Okay? All right, so let's interpret the results. So, if you remember a few classes ago, I said that when you do an ANOVA, like you really can't say that this mean is greater than that mean. All you can really say is that the means are different, right? Unless you have one factor with two levels, then it's obvious. If that factor is significant and you only have two levels, well, it's obvious which one is greater than the other one because there are only two. But when you have multiple levels, ANOVA by itself doesn't tell you which of those levels differ from the other ones. All it tells you is that there is a difference between some of the levels, right? So you don't know. So what we need to do is do a post-hoc test. Post-hoc means like follow-up test. We're doing it after we've computed an earlier test. So we computed our ANOVA, now we're going to do a post-hoc test. Now, you're only going to do post-hoc tests if the initial ANOVA is significant. Because the ANOVA, when we set our alpha for the ANOVA, it controls our alpha error rate. And if we go in and we start doing tests, after we do an ANOVA that was non-significant, we might find differences that are significant anyway. Which means that potentially we capitalize on chance. So we want to run ANOVA first to tell us whether some factor is a significant predictor or whether the interaction of some factors is a significant predictor. And then once we know that it's significant, then we can go in and do follow-up tests. So how can we test to see which means are different? T-test, right? Is this mean different from that mean? Well, that's two means. Use a t-test. Use an independent t-test here. We haven't talked about repeated measures, which would be equivalent to the dependent t-test. But we could do t-tests. We know how to do them. They're pretty easy. You need to get the data in an appropriate format, so you could use sort of what I did earlier. Get the response time data for this set of levels and compare that to the response time data for this other set of levels. So we could do that. Now t-tests are commonly used as a follow-up for significant ANOVA, but there's a problem. Can anyone tell me what the problem is? Does anyone know? Let's say we had three factors, right? I'm sorry, we had a factor with three levels. This means there will be three different means, right? How many t-tests could we use to compare those means? Two. We compare these two, we can compare these two.
And the other one?
We can also compare those two, right? So we could use multiple t-tests, more than one t-test. Now when we specify alpha for a t-test, we're saying we want to limit our alpha error to this level, right? Now that will set the alpha level for each t-test to that level. So what happens if you run multiple t-tests? You will have more alpha error, potentially, right? So when we do multiple t-tests, we're going to inflate the overall alpha error rate. What will we do? What will we do? We need it better. We're going to use Tukey's honestly significant differences. Tukey's honestly significant differences. So Tukey was a person, and he came up with a way to figure out whether a difference was really significant or not. Basically what it does is it adjusts for this inflation that doing multiple t-tests does. It's basically like a t-test. So with the t-test, we took differences between means, right? So x1 minus x2, and we divided it by some standard error, right? we're doing exactly the same thing with the t-test, and we're adjusting the probabilities for the number of comparisons that we're making. Now, I'm not going to cover the specifics about how you get each standard error for the different comparisons that you might make, because R will do this for us. So this is one instance where I feel kind of bad because I'm not going through all of the steps. But I think we already have enough level of difficulty for us. So try this. Tukey, HSD, AD. Oof! You see a lot of data?
Yes.
So, like, this is the start, and I stopped here, but this only starts looking at the interaction between target features and display size. So this hasn't even gotten into the other interactions, or the three-way interactions. With the three-way interaction, we have three different factors with multiple different levels. There are lots and lots and lots of means that we can compare to each other, right? So we could potentially do lots and lots of t-tests, which would be a bad idea. But by using Tukey's honestly significant differences, it tells us the significance, or the p-value, for each pair of means that have been specified in the model that you created. So this is going to give us the differences between all of the different means. Okay? So it's a lot.
So what will you do with it?
What will you do with this? What could you do with this? Let's see. Now, if I ask you the difference between display sizes 5 and 15, whether those are significantly different, you can tell me. So, are the display sizes 5 and 15 significantly different from one another? So in the overall ANOVA, there was a significant effect of display size. Is the difference between display size 5 and display size 15, is that significant? The difference is 453. Mine is a little goofy because I was working with S5. I changed it, so it's SO5. So you should have the positive version of this. 453, right? So that's the difference between those two means. Is that difference significant? I haven't told you how to figure that out yet, but I think you know enough to figure it out by yourselves. How can you figure it out? Here's the difference between the means, or here are the means that you're getting the difference for. There's the difference. We see LWR, UPR, and then P, ADJ. Do you think? Which part?
Lower critical value.
Lower and upper? These are actually confidence intervals for the difference.
So it's not significant.
So it's not significant. The question is, so if the confidence interval contains 0, then it wouldn't be significant, right? Does the confidence interval contain 0? So lower and upper, this should actually be flipped because I did it goofily until I fixed the data set. So you have, the difference, you have a difference of 453. The 95% upper critical limit is 619, and the lower limit is 287. Is 0 within this range?
No.
No, 0 is like way over here. What's the p-value?
0. Close to 0. Almost.
Yeah, it's ridiculously close to 0.
So when you fail to reject,
What would we do?
you have to fail or reject.
When p is less than alpha, what do you do? Reject. The hypothesized difference is 0. Remember back to our null hypothesis? We said all of the means are equal, which means that the difference between any two of the means is 0, right? And 0 is not within our confidence interval. So by doing Tukey HSD, we get an indication about whether a specific difference is significant or not. So this tells us about the difference between set size 15 and set size 5. And yes, this is significant. It's beneath our alpha. And more than that, it gives us a confidence interval. So if I ask you to create a confidence interval for the difference between people that had a target with common features and a set size 30 versus common features and a set size 15, you just need to find it. Here it is. Is that difference significant?
Yes.
Is it less than 0.05? Yeah, it's a lot less than 0.05. Not all of them are. So this one, this first one here, that's not significant, right? Groovy. Now, by default, this gives you a 95% confidence interval.
So what do you do if you want?
So if you want a 99.1, what would you do?
What do you do?
I'm hoping this is right. Okay, Tukey HSD AV comp level. Yay! So remember how we did the confidence levels before? Where are we? Oh, so much data. Boom. Now we've used a 99% confidence level, which will give us a 99% confidence interval. Sweet. Cool. Okay. So, you can figure out which differences are significant. You can also figure out which difference or which mean is bigger, right? So if this is positive, then that means that the first mean is bigger. If it's negative, that means that the second mean is bigger, right? Cool. Another note on interpretation. If there's a main effect and Tukey's honestly significant difference reveals some difference, like it did for unique and common. So it's saying that common was 388 seconds slower than unique. I think we're.
And the second was not the main effect. I mean for previous one.
This?
If there's a main effect.
So a main effect. What's a main effect? We talked about this last class. You just distinguish between main effects and interactions. Subtract what? Okay, if we wanted to find whether or not there was a main effect, we need to calculate the sum of squares, and we would do that by finding the mean for each level of that factor, and then subtracting the grand mean from it, squaring those differences, and multiplying appropriately. That will give us the sum of squares, and we can divide it by the degrees of freedom, which gives us a mean squares, which we can compare to the mean squares for the error, which gives us an F ratio, which, if it's significant, means that there is an effect of that factor. The main effect means that there is an effect of some factor by itself. Okay? So we have main effects. It's an effect of the factor by itself. We have interactions, which is an effect of the two factors interacting, which is rephrased differently, means that the effect of one factor depends on the level of some other factor. Or some other combination of factors, right? Do you remember that, I hope? That's the main effect. So, Tukey's honestly significant difference. Actually, the initial summary.AOV told us that there was a main effect, and Tukey's honestly significant difference said that common is slower than unique, right? Slower meaning there was a longer response time, a bigger response time. So, common was slower. So you might want to say that common is always slower. And it's always slower by 388 milliseconds, right? Because that's the difference between common and unique. But there's a problem with that. We can only conclude that the means are different by about that difference when there are no interactions involving that factor. Right? The main effect, if there are no interactions, then that means that that effect is basically what it is by itself. But when there's an interaction involving that factor, that means that its effect actually depends on something else. It's not constant, it varies. Right? So we can only conclude that the means are different by some certain amount if there are no interactions. If there's an interaction, it varies. We might be able to speak generally, like generally speaking, targets with common features are slower than targets with unique features. Right? Generally, I didn't talk about the specific size. Okay, so the rest has to do with visualizing the results, which you are not actually going to need to do for any of the homework, although I like looking at them. So I'm just going to skim through this, and you can do it a little bit later if you want. I've introduced a new function, use, yay, and you can come up with a nice graph that looks something like this. So on the x-axis, we have our display size, 5, 15, 30. On our y-axis, we have response times. Actually, the response times for different means, for each mean for each condition. Now, the conditions, the red lines indicate when the target was absent. So like stop, don't do anything if it's absent. Make more sense. The dashed lines indicate searches where all of the features were common. So we can look and we can see some things. So generally, the reds are above the black, right? Indicating that there should be a main effect of target presence. There was. We can also see that generally, if you compare the same colored lines, we have the dashed lines are underneath the solid ones. So the dashed lines were the ones for the, I'm sorry, I said common, but the dashed lines are for the unique, the target with a unique feature. So targets with unique features are generally faster, right? And we can't say exactly how fast it is because it depends on what condition that we're in. And we also have the interaction. So the target present, those would be the, which one? The black ones. They seem to increase more slowly than the red ones do, right? That makes those lines not parallel. Those are the interactions. So you can use the visualizations along with the summary and with the Tukey's honestly significant difference information to try to figure out exactly what's going on with your results. All right. I'll stick around, answer questions. I got a whole bunch of emails about homework problem 11 and homework 19. So we can talk about that if you guys are interested. I'll turn